Greetings and welcome to another lecture in comparative psychology. Now, a lot of this particular lecture is going to deal with what are known as game theory models. We talked about game theory when we were talking about prior subjects in terms of things like, cooperation and that sort of thing. And so a lot of the theories for aggression also deal with game theory. Now, they all have something in common. They all have a cost to fighting. Whether the cost of fighting is a physical cost where the individual might be injured or killed, whether it's a cost of fighting about a time cost where it's time where they might otherwise be foraging or sleeping or taking care of offspring or whatever. It may be a cost to their future genetic legacy. I mean, there are all sorts of costs, but all assume that fighting has a cost. There's also some sort of variable that represents the value of what is being fought over. Remember, aggression can basically take place for all sorts of things. It can take place over resources that are food, that are shelter, that are mates, that are, whatever. There's all sorts of resources. So this can vary. I mean, it can vary even within something like food. That can vary. The value of a particular food item might vary as to how hungry the individual is, or how common the food items are, or any of a number of other things, defending territory, defending offspring, value of fighting versus fleeing. I mean, there are all sorts of variables here. Everything varies, everything needs to be weighed, which is why most of these are some sort of mathematical model. And I will tell you right now that I don't care that you know the mathematical model. I'd rather, you don't need to know the formulas for this. This is something that is complicated enough and has enough variables that vary that on this level, all I really want you to know is how these work. For the most part, when they're presenting the math, they're presenting it to show, see, this is how this would predict that. I don't care about that. I really don't. I just care that you know what these models are, that you know what examples of them, that you know how they work. You don't need to be able to prove to me using math exactly how they work. The first model we're going to talk about is called the hawk-dove game. Now, this is going under the usual view of a hawk being something that is going to be aggressive, that is going to want to fight on some level, and the dove being a more peaceable creature that perhaps is more interested in fleeing, or perhaps more interested simply in submitting and not fighting. So here the hawk is an individual. It's a role, basically. Since these are game theory, these are all roles. It's a role that involves the individual escalating until they get what they want or until they're injured to the point where they can no longer fight. That may be injured, that may be dead. Either way, they can no longer participate. So they basically fight until they get it or until they're out. Doves, on the other hand, are threateners. Doves will act like they're going to escalate. They'll talk a big game, but if their opponent escalates this and is basically, if their opponent is a hawk, then they are going to back off and give up and not fight. So they're all talk and no action, essentially. Now, how this plays out depends on who is fighting who is matching up with who. If you have, and again, if you think about each of these roles, you could probably predict what each of these matches are going to wind up with. If you have a hawk-hawk fight, then they're going to fight until one retreats or can no longer fight. And so in this case, one is going to get 100% of the resource, the other is injured. The other is going to have a cost. Not only do they not get the benefit, but they get a cost. With hawk and dove, the hawk, threatens, the dove threatens, the hawk escalates, the dove gives up, the hawk gets everything, but the dove is not injured. So there is no cost other than the cost of losing whatever the resource is. There's no physical cost to that, as opposed to hawk-hawk, where basically they both fight until one is too injured to move on, and then the other gets everything. There's dove-dove. With dove-dove, what happens is one escalates. They each threaten, neither escalates, so they basically split the resource 50-50. Nobody gets hurt. And if this is beginning to sound a little bit like the prisoner's dilemma that we talked about in terms of cooperating, you're exactly right. It's another version of the prisoner's dilemma, which is if I don't fight and you don't fight, then we each get half the resource. On the other hand, if I fight and you don't fight, I get everything. On the other hand, if we both fight and I win, I get everything, but if I lose, I'm hurt and I don't get anything. So, yeah, it's a variation of the prisoner's dilemma. Now, just like when we were talking about the prisoner's dilemma, there's also the evolutionarily stable strategy, or ESS. And so how to determine which role to play, the same as with the prisoner's dilemma, depends on basically cost versus benefit, or in this case, the cost versus the value of what you're fighting over. And the idea here is that if the value of the resource is greater than the cost, okay, if the cost of gaining the resource or the cost of losing is death, for instance, then it makes sense to always be a hawk. Okay, this is an evolutionarily stable strategy. If the value of the resource is greater than the cost that you're going to get, that it's going to cost you, then it always makes sense to be a hawk. Because, you know, if you win, then, and even if you're injured, you still have the value, and that's more important. So the idea here is that if the value is greater than the possible cost, you should always fight. You should always be a hawk. Now, if the cost is greater than the value, then neither is an evolutionarily stable strategy. It's a crapshoot. Sometimes it would make sense to be a hawk, you know, if you can kind of predict that your opponent is a dove. Okay. Sometimes it makes sense to be a dove if your opponent is a dove. On the other hand, if your opponent is a hawk, it's going to make sense then to fight, but it depends. Okay. Because if you lose, then the cost is going to be a problem. If you don't win, then even if you're not injured, the cost could very well be a problem. So you want to make sure that what you're fighting for is worth the cost. If it's worth the cost, you're probably going to fight and fight to the death. If it's not worth the cause, you're much more likely to just back off and either give up on it or hope that your opponent is a dove. The next model is called the War of Attrition Model. And a war of attrition is basically, attrition is usually thought of as you kind of grind the other person down. Okay? So we're going to work with attrition. And actually the war of attrition here is more about threatening than actual fighting. Okay? So it's more about I'm going to threaten and threaten and threaten until I freak you out. And you're going to threaten and threaten and threaten until hopefully you freak me out. There usually isn't any actual fighting. Now this display has a cost. This threatening has a cost. Okay. Presumably it's less of a cost than fighting would have. But it's a cost in energy, it's a cost in time. Like I said, it doesn't necessarily being a cost in actual injuries, although I'm sure that could take place. But it has a cost. And with this one, there's no clear cues about how it's going to settle. You don't know what sort of threatening is going to settle it. You don't know when your opponent is going to back off, and you may not exactly be sure what would make you back off. So in this case, there's a lot of what in humans, we call saber rattling. There's a lot of threatening in the hope that you're going to freak the other person out. And quite frankly, a lot of animals do this. If you watch the wolf video, you'll notice that a lot of what they do is not actual attacking. It's threatening. Okay? It's threatening. I'm going to be bigger than you. I'm going to be stronger than you. I'm going to freak you out. I'm going to show you all of these efforts that if we did fight, I would just kick your butt. And so there's an awful lot of displaying because threatening may have a cost, but it's less of a cost than fighting. Now, how long they fight, how long it makes sense to threaten, I should say, how long it makes sense to keep this war of attrition going on, that's where the math comes in. And so that's what I'm going to say that you don't really need to know. You need to know examples as always, but you don't really need to know the exact length that they're going to fight. You don't need to be able to use the formula because it's not needed for this. But you do need to know that the evolutionarily stable strategy here varies. It isn't as simple as, always be a hawk or whatever. It varies. And so it will depend on the cost, it'll depend on the benefits, it will depend on the length of the contest along with the cost. I mean, there's all sorts of things that go along with the possible costs here. The next model is the sequential assessment model. Now, the sequential assessment model is it's almost a cross between the two in that it tends to involve perhaps more individual combat or certainly more threatening. Okay, there's a lot of engaging with others here, I should say. And so in this sort of model, the individuals are constantly assessing one another. They're constantly testing one another. They're constantly poking at the other to see what that poke is going to do. Are they going to fight back or are they going to back off? And a lot of times this happens when we're talking about hierarchies, when we're talking about those dominance hierarchies. Who's higher on the pecking order? Who's more dominant? Who's more in charge? Who's at the bottom? Who will always give up? And so whenever there is this sort of thing, they're constantly testing. And I hate to bring up wolves again, but wolves are another great example of this because wolves have a hierarchy and wolves are constantly testing. It's part of the reason why the dominant animals are sort of constantly throwing their weight around, are constantly showing the others, don't test me because I'm still bigger and stronger than you and I'll still win. So it's part of this sequential assessment. So the lower ranking are constantly kind of poking the higher ranking to see if there's any signs of weakness, to see if there's any sign that a fight might actually make sense. And there may even be actual fights, small fights, low stakes, probably not a lot of cost in comparison to the benefit of knowing exactly where that individual stands. Until eventually one of the combatants, whether it's, constantly testing each other, one will realize that it will lose this fight. And because it will lose this fight, there's no real reason for it to keep going. And it will stop poking the bear, as it were. Now, the evolutionarily stable strategy here, particularly in hierarchy, is start small and work your way up. Start with somebody who might be just slightly more dominant than you. It doesn't make sense if you're a non-dominant animal to try to go and overthrow the king, because the king is very likely to kick your butt and probably hurt you, maybe kill you, maybe drive you out of the pack. That would be a bad thing. So start small, work your way up. Now, granted, if you poke the king might be much more likely to stop once they've basically shown you that you are not going to win. And in fact, in these cases, very often, the most dangerous bouts are the ones where the combatants are most evenly matched, because it's much less likely that one will convince the other to give up. If you're more very evenly matched with another individual, then they're not going to overwhelm you or you're not going to overwhelm them. And so there's nothing that's going to convince one or the other of the combatants that it's time to give up. And so therefore these fights tend to continue and they tend to get very dangerous and they tend to get very deadly in some cases because being evenly matched each is not going to convince the other through non-dangerous means to give up. So in a way, these can be more dangerous than some of the other models, simply because, as I mentioned before, one individual is much less likely to completely convince the other to give up. And so these are the basic models that we have in terms of looking at game theory and aggression.